Okay, so introduction. Skylab was the first U.S. space station that was launched and put into orbit on May 14th of 1973, being launched from the Kennedy Space Station as part of the Saturn V rocket. Skylab had the main objective and goal of studying the effects of living in space for an extended period of time. There were 3 successful manned missions on board with a total of 9 individuals being on board during this test. The satellite was in orbit for 2,249 days and completed 34,981 orbits up until June 11th, 1979, when it crashed back down to Earth.
Findings by Skylab. Before Skylab, the US never experimented with long-term space missions. One of Skylab's main purposes was to prove that humans can live and work in space. Over the course of 3 missions, it was proven, with each of the missions being rendered a success despite mechanical issues. Another one of Skylab's missions was to help us with getting a better comprehension of our solar system by collecting data without the interference of Earth's atmosphere. As seen on the next slide, a negative image of the comet Kohoutek taken on a spacewalk Christmas of 1973, as well as documenting a solar flare in unprecedented detail, being the best photograph of one at the time. Valuable additional data was provided by remote sensing of the Earth from orbital altitudes, along with photography in the visible and near-infrared spectral regions. The advantages of spatial observations were the large field of view offered by the increase in altitude, the frequent coverage of the same area, and the coverage of areas otherwise inaccessible.
So here we have some images of the Skylab and some satellite images they took as well. Um, for being a satellite in the 70s, it was a pretty big deal, but compared to today's standards, the satellite spanned with a length of 82.4 feet with a length and a width of 55 feet. So back then that was a pretty big deal, but compared to today's standards, not the biggest.
Instruments on board included an orbital workshop, which was a multi-floor capsule that served as a base of operations for the crew, serving as both living quarters and a laboratory. It also had an Apollo telescope mount, which is designed and built for Skylab. It's an orbital observatory used to research the sun, stars, Earth, and distant planets with no atmospheric interference. It also has solar array panels for energy and power, or for minor movements not using fuel.
Before we move on to the actual calculations and the equations, it's best to actually find out what we will need to calculate these, including the equations and the different components of the equations. So starting out, we have the mass of Earth, which can be calculated at 6 times 10 to the negative 11th, and that's how you calculate the mass of Earth in kilograms. The universal gravitation number would be 6.67 times 10 to the negative 11th. To calculate orbital period, it will be 2 pi r over v. And then you have the orbital velocity, which would be the square root of g times n plus m over r. And r will be equivalent to the distances to the center of the Earth, which will be the altitude of the satellite plus the radius of Earth, and also the mass of Skylab, which is 76,540 kilograms. Now moving on, so we're going to be calculating now the orbital period of the satellite in seconds. So to calculate the orbital period, we're going to use the equation before of 2 pi r over v to find p, which is the period of the satellite. So plugging in the numbers we have from before, we know that r would be the radius from the satellite to the center of the Earth, so that would be 435 plus 6.4 times 10 to the 6th in kilometers, over the velocity of the satellite, which we just calculated on the last page, which will be 7,907.4016. And after we plug that into the calculator, we found out that the orbital period of the satellite is 5,085 seconds. 5,085.75. Now moving on, so we're going to be calculating now the orbital period of the satellite in seconds. So to calculate the orbital period, we're going to use the equation before of 2 pi r over v to find p, which is the period of the satellite. So plugging in the numbers we have from before, we know that r would be the radius from the satellite to the center of the Earth, So that would be 435 plus 6.4 times 10 to the 6th in kilometers over the velocity of the satellite, which we just calculated on the last page, which will be 7,907.4016. And after we plug that into the calculator, we found out that the orbital period of the satellite is 5,085.7565 seconds. So this slide right here is just a basic slide with just the two numbers that we just calculated before, just to put them together and just show them both in the same slide. So we have the orbital velocity in meters per second, and we also have the calculated orbital period. So now on this slide, it's shown the model of the satellite which we made. So a little bit about the model of the satellite. Using Blender, we were able to make a scaled model of the satellite. Blender is a 3D modeling tool. It's free and open source. It's a very powerful tool. So once this model was complete, we were able to export it into an STL file in order to 3D print it. Now, before 3D printing it, we did have to use support, as it would not be able to print as one object without it. Sadly, the support stuck to it, so now it's standing on stilts, but you know, it's still cool in my opinion. Now, as per accuracy per se for the satellite would be considered accurate to me as a model because using the NASA specifications and NASA models of the satellite, we were able to construct it by using the exact specifications and dimensions and information, all from the NASA website. So the final slide we have is just the sources used. So